So coming back to this waveforms, you can see this waveform C is my ramp and pedestal waveform, which is generated by that particular block which we have in the demodulator. Now, ramp and pedestal waveform is nothing but a waveform in which you have a ramp signal, that means linearly increasing signal, and then remaining part of the signal will be constant. Again, in the second cycle, you have a linear part and then constant, linear part and constant part, and so on. How much amount of time the signal generates linear part and how much amount of time signal remains constant depends upon the width of the incoming pulse. Till the time width is present, the circuit will generate the linear waveform, and when the pulse is absent, the circuit will keep the output constant to that particular last value. When the next cycle begins, the block will start from 0 now, generate the linear waveform till the time pulse is present, and whenever the pulse is absent, now the block will keep the output constant. And this is how this particular waveform is generated. The second block will generate the reference pulses. You can see these are the reference pulses generated, and the reference pulses are generated at the end of the pulse cycle. So this is my one cycle, this is another cycle, third cycle, etc. At the end of the cycle, the pulses of constant amplitudes are generated using the reference pulse generator. So how can this be done? The reference pulse generator will first generate pulse at the beginning only, when the original pulse in PWM signal starts, but then all it has to do is delay that particular pulse by this much amount of time so that it is pushed to the end of the cycle. And once we get these two waveforms, we are going to add them using an adder. So output of the adder will look something like this. Wherever that constant part in ramp pedestal waveform occurs, that constant part will be added with this constant amplitude pulse, and hence you will see the sudden rise in that final output of the constant part. So this is the output of the adder that we get. Please note that it is the result of addition of these two signals. And once we are done with this, now if you observe, in the first case, the amplitude of the entire output of the adder is not very large compared to the second case. In second case, it is very large because in the second cycle, the ramp signal remains for a longer amount of time, and hence that constant output of the signal was large compared to the previous case. Now, if you add pulse to that, obviously the final output will also be more. And what was the reason the ramp signal remains for higher time was the higher width of the pulse. So in short, whenever you have a pulse with higher width in PWM signal, then you will get the output of the adder also with very large amplitude. If I now apply a clipping level, if I give this output to a clipper, because that's my next block now, the output of the adder goes to the clipper, and we are saying that output of the clipper is nothing but PAM signals. So if you see, if I give this to a clipper and if this dotted line is a clipping level, everything below this will be clipped off, and I will only keep the portion above the dotted line. So this is my output of the clipper. And what you observe is output is in the form of pulses of constant width, but amplitude of pulses is changing. And if you observe carefully, the amplitude of pulse is not changing randomly. It will change in proportion to the width of the PWM pulse. I hope that is clear to everyone. And hence, we can conclude that the output signal, the pulses, have the amplitude proportional to the width of the pulses in PWM signal. And because the width contains the information is now present in the amplitude of this final signal, and hence what we have got is PAM. So we have converted PWM signal to PAM signal, and now all we have to do is pass that signal through a low pass filter. So my output will be nothing but demodulated signal.